full screen now.
Okay, good.
Thank you.
So Andres, thank you for the invitation. Nice to be with you for explaining what we are doing on the NBQ module in the Strait of Gibraltar to see the dynamics of the straits, the small scale dynamics. So I will present several applications of this NBQ module that have been developed in the group in Toulouse. And I will thank all the co-authors of this presentation and all the sponsors as well. So we'll talk about the Strait of Gibraltar. This is a narrow passage that connects the Atlantic Ocean with the Mediterranean Sea, here in the blue box over the map. This strait is the unique entrance of the Mediterranean Sea, which is a semi-enclosed sea between Europe and Africa. And the strait is bordered by Spain and the British territory of Gibraltar in the north, and by the African country of Morocco and the Spanish exclave of Ceuta in the south. The strait features great importance for economic activities for the countries of both continents, and also important defense activities. This strait is about 60 kilometers long and has a width of about 13 kilometers at its narrowest point. The western end is located between Spain and Morocco and has a width of about 40 kilometers. And the eastern end is about 23 kilometers. The depths range between from 300 meters at Espartel here, and to 900 meters at the eastern end. So this narrow straits connect the Atlantic Ocean with the Mediterranean Sea. It features the Gulf of Cadiz at the western end of the strait, and the Alboran Sea, then the Algerian basin in the Mediterranean Sea. From an ocean circulation point of view, a significant amount of water is exchanged through the Strait of Gibraltar to balance the ocean atmosphere fluxes over the Mediterranean Sea. And because of evaporation and precipitation imbalance over the Mediterranean Sea, the Atlantic Ocean and the Mediterranean Sea have different salinity levels. And therefore, the highly saline water from the Mediterranean Sea flow outward and in depth. This is the Mediterranean jet in red, whereas the less saline Atlantic waters flow inward and on top of the Mediterranean Sea current, and this is the Atlantic jet here in blue. Another interesting feature in the Alboran Sea is two anticyclonic gyres that will be out of the scope of this presentation. And the latest process that interests us in this talk is the large tides from the Atlantic, the North Atlantic Ocean. So this talk will only focus on small-scale processes that are occurring within the strait. This, I mean, with typical land scales at less than 1 kilometer. So as I said, the ocean circulation within the strait is a two-way exchange, directly influenced by the interaction between the intense tidal forcing from the Atlantic Ocean and the complex geometry of the strait. You can see different seals here. And this interaction is made through the mixing mechanism. So several small-scale phenomena contribute to this mixing. You have this small amplitude internal gravity waves at the interface of the Atlantic waters and the Mediterranean waters. B, you have this hydraulic control mainly done at the Camarines seal caused by tidal currents, and consequently you have a recurring hydraulic jump. C, here you have shear instabilities in the Mediterranean vein. And D, when the hydraulic jump is released during inflow conditions, you have an energy propagation eastward at the train of internal solitary waves here at the interface. So the surface signature of these internal solitary waves can be waves from space, can be seen from space. This is mainly seen from the pioneering works of Alpers in 1996 from ERS-1 synthetic aperture radar instrument. You can see here the same with the latest SAR radar from European Space Agency. You can observe this surface signature as well with hyperspectral imagery with different missions and different imager. You can see also this surface signature here from the ISS, the International Space Station, or with the Pleiad optical imager. And you can use also optical imagery to study the surface characteristic of the hydraulic jump. You can see here the surface signature of the jump, and here from the research vessel Latalent during 2002 campaign, you can see boiling waters directly from the ship. So to study the flow dynamics in the strait in further detail, in particular this interior ocean, realistic numerical modeling is of great help. You have early attempts using two-layer models in the 19th and early of the century. The increase of the computational power led to 3D modeling with increasing vertical and horizontal resolution, explicitly addressing the tidal cycle and the flow characteristics. Then some aspects of the straits could not be well reproduced by these numerical models, especially the evolution of the internal tidal bore generated at the Camarines seal. So this model requires fully non-hydrostatic codes and physics. So more recently, non-hydrostatic models have been used to explicitly represent the internal solitary waves, like in Sanchez-Garrido and Salino works. And we complement here this list with the state-of-the-art CROCO model, the non-hydrostatic compressible approach presented just before by Patrick, based on the relaxation of the Boussinesq approximation instead of solving the Poisson solver. And you have now a fully 3D fast mode solver resolving all waves down to acoustic waves. So this NH solver can be used in problems from a few tenths of meters, like for LES or DNS resolution. And like Patrick said, this new model, this new code, come with monotonicity preserving advection scheme like WinU5 or TPD, and fully 3D turbulent closure schemes. So for us, it's a perfect candidate for modeling the dynamics within the Strait of Gibraltar. So after this introduction, we will review some interesting features of this NBQ model available in the CROCO code in application to what can be called the main benchmark of our group, the Gibraltar Strait. So first, we'll see a 2D vertical slice model option, which can be nice for investigating some non-hydrostatic details. Then a full 3D model option for nearly LES and the route to the turbulence. And finally, we'll see the mesh refinement capability brought by the Agrif library provided with CROCO for the study of ocean scale interaction. So the first application is using a two-dimensional vertical section of the Strait of Gibraltar. And it's interesting to numerically investigate some detail of the small scale dynamics. It's quite simple, it's computationally efficient, and it incorporates the configuration of the seal, the different seals of the region. So the grid feature 50 meter horizontal resolution along the x-axis, and the x-axis is this line which represents the transect defined by Farmer and Army for the Gibraltar experiment campaign in 1988. We have 40 sigma level along the vertical dimension. The model also features a high resolution bathymetry with a native resolution of 100 meters. And this configuration grid has been developed by adapting the CROCO tools routine and creating a specific mate bathy grid routine. The stratification in temperature and salinity profiles is adapted from the work of Bryden et al. And the model is started with a lock exchange mechanism following the initiative by Semino et al. Tides are adjusted directly in the Fortran file CLM tides to feed values from the TPXO 8 atlas. So well, last point, there is no atmospheric forcing in this simulation. So after a 3-day spin up, we run a 5-day run with 1 second time step for the slow mode and 1/8 second time step for the fast mode. Here are the main CPP keys for this model. For sure, you define the NBQ CPP key. You can use the default key NBQ perf. Have in mind that these keys are fully compatible with the S2DV CPP keys. There is no change. You can use the same configuration with the S2DV key. Then you use a new S chord for the vertical coordinate and masking key for using the topography. We use our own tidal forcing with the NS periodic CPP key. And in the advection section, as Patrick, I will advocate for dedicated advection schemes such as TVD or Uno 5 if you use subgrid scale closure, such as GLS. As Patrick has shown, you have you will remove all oscillation using this shock capturing schemes. So here we compare two S2DV simulation. On the right, you have a classical hydrostatic simulation of the strait with a 200 meter resolution on the horizontal, which is more or less the resolution of the OGCM in the region. And on the right, you have the NBQ simulation described previously. We have a particular focus here on the shear instability occurring at Camarinal seal at the onset of the tidal outflow. And I will present here the contour of vertical velocity in a blue-red palette with isopycnal surfaces overlaid. If we look at the NBQ simulation, you can see explicit primary instabilities that have been identified as Kelvin-Helmholtz type instabilities, developing here at the interface of the Mediterranean and Atlantic water. These instabilities are the starting point of the direct turbulent energy cascade, transferring energy from the large scale of motion to the small scale. Obviously, there is no small structure like that in the hydrostatic simulation here. But we'll see here that this is not just a story of putting the key NBQ or not. This is not a story only of high enough resolution on the horizontal. We'll show here the same kind of contour. This time, this is a contour of y-axis vorticity in grayscale, still with isopycnal surfaces overlaid, and still at the beginning of the tidal outflow. If we break down this plot, the NH simulation at 200 meter resolution here does not feature shear instabilities. And you compare with this one, which is the same of previously, you can see here the instabilities developing at here in the lee of the seal. If you look at this one, this is the hydrostatic simulation at the same 50 meter resolution. You don't see a resolution. You don't see instabilities. So the message is this is not a story of NH physics or high enough resolution. You need to have both physics and high resolution to go on the way to turbulence. If we now have a look to internal solitary waves generated by the release of the jump here, we represent on this panel the velocity fields and isopycnal surfaces after 3 days of spin-up. And we can see a train of 4 mode 1 waves propagating eastward. The amplitude of the first wave reaches 100 meters, and the solitude, the soliton train amplitude increases then and exceed 150 meters. as it propagates here over the slope of Strait NH. And then the wave amplitude decreases, and as the train propagates toward the deeper region. In this part of this plot, you can see the depth evolution of this white isopycnal surface as a space and time diagram. Time is there, and space. Region of sharp horizontal density gradient can be identified periodically in the region of Reional, and then they correspond to the generation of hydraulic jump, and the propagation of internal waves are identified by the tilt of isoline, whose slopes provide an estimate of the wave propagation speed. This one and that one. In this slide, we present on the left the density anomaly fields in the region of Tarif and Narrow. Late in the simulation, at time is about 8 periods of M2, something like 4 days after spin-up. On the top panel, you will have the same hydrostatic simulation as before, as a 220 meter resolution. And this is the non-hydrostatic simulation of 50 meters. We can see that mode 1 and mode 2 large amplitude internal waves are generated at the Reional seal here, and propagate eastward during each ebb of in both simulation. However, only in the non-hydrostatic simulation you can see a wave train propagating. In this hydrostatic case, the lack of non-hydrostatic dispersion produces internal waves that are propagating as internal bore. Here, the waves are propagating as strain of solitons with a varying number of solitons and celerities. In this right figure, we illustrate that the train propagation that is external from there is quite comparable with SAR observation from space. So we have seen here a nice and efficient way to make primary investigation of the small-scale feature of the Strait of Gibraltar. Trust me, but this capability, this S2TV capability, is really computationally efficient. You can run very easily and efficiently nice simulation to start on your investigation. And the characteristic of the simulated internal wave were found compare qualitatively well with published observation and previous numerical studies. So despite the shortcomings of this 2D representation, this configuration provides a realistic depiction of the mechanism occurring in the strait. So based on this work, we move on the full 3D model of the Gibraltar Strait. This model has been developed with the same horizontal resolution of 50 meters now in both X and Y directions. We will use the same high resolution bathymetry, which is shown here. The lateral and initial condition are provided by the Mediterranean system from ENEA organization. The tidal forcing provided include 4 constituents, namely M2, S2, P1, and O1. And we still do not apply wind forcing nor atmospheric forcing fluxes for this simulation. Note that we have done some adaptation to the CROCO tools MATLAB routine to be able to take into account large grids and as well interpolation and masking issues on this very, very small scale grid. For this model, we run 2 days spin-up with the hydrodynamic version of CROCO. Then we run a 4-day simulation with the NBQ module. Here are the keys, same as before. You define NBQ and NBQ perf, CPP keys. You use TVD and Weno scheme for advection. You define tides as well. Here I will show you an animation of the z-axis vorticity field of surface currents. You can see several areas of hydraulic control. The main control is here at over Reional seal and Spartel seal. You have the formation of hydraulic jump, then its relaxation over each tidal cycle. Another formation, and then the relaxation. Those solitary waves are observed after the relaxation, like we said, and after the relaxation, you have a train of internal waves that can be observed periodically at each tidal cycle, and the train propagates through the slate. Then goes out the domain. You have a nice interaction here in the small vortex, and you can see reflection as well, and other also. If we look here, vertical section over the Reional seal, this is the section, you have the tidal cycle, and this is a sea surface anomaly map here. So you have the Reional seal, the contour of vorticities are in color. You have the direction of the flow with white arrow, and the hydropicnal surfaces are in black lines. So this animation, and I have a blowout. Sorry, we'll start it again. Excuse me for this trouble.
Hello.
Okay. Sorry. Yeah. Is everybody okay with the presentation? Can see it? So this is the animation of the control of the flow over each tidal period. You have the hydraulic control here, then the generation and the relaxation of the hydraulic jump. You can see now the relaxation and the propagation of larger amplitude internal solitary wave. What is interesting is the shear instabilities developing there. That are amplified when the jump is active, and we will see at the surface what we call the boiling waters. Yeah, at this time now. So this is the transect of from the 3D, the full 3D model. So this 3D simulation allows us to investigate shear instabilities in the density flow west of the Reional seal. So the seal here and the tidal cycle. During the tidal outflow. So for this investigation, Margot has proposed a diagnostic based on the Q parameter, which is a second time variant of the velocity gradient tensor. It can be seen as the 3D generalization of the Okubo-Weiss parameter, which measures the relative importance of deformation versus rotation. So when this Q parameter is strictly positive, rotation is larger than shear. So this animation represents the evolution of this parameter for a value of 10-4 in red. Over a surface content of salinity in green. The temporal evolution of Q shows oscillation between high values in red, the center of the below, and low negative values. This shared layer between two consecutive belows, for instance. So this kind of structure are numerous between the Mediterranean vein and the Atlantic waters. And they are carried westward by the Mediterranean outflow. So as a wrap-up of this 3D capability, we have seen the extension of previous results on shear instabilities from now a 3D model. So I will insist in this conclusion of the new diagnostic that have been developed, such as actually the Q parameter for the detection of shear instability. It's really new, and it's something that we need when we go to LES simulation. And there will be a new metric coming soon for the dioptical mixing evaluation that is called BPE for background potential energy. So these metrics and maybe others are essential to evaluate this new LES model and then go toward a better representation of diurnal mixing in the ocean and in climate models. In this final part of the talk, we see another development in the NDQ module, which is the grid refinement using the AGRIF library that is already used in the CROCO hydrodynamic kernel. Briefly, we have introduced a two-way exchange for MBQ variable at the fast mode. And we have tested it on the classical vortex implementation test case. This is an ideal experiment of a baroclinic and asymmetric vortex that propagates on a beta plane. So in this test, the grid refinement is implemented at the center of the square domain, and we get the free evolution of the vortex. We have tested one-way and two-way nesting in this configuration, and here we see the surface evolution contour of the vortex from the parent grid, which is over the whole domain, and the dashed the lines, and the surface elevation in the child grid region, the center part of the domain, with evolution in a solid isoline. And you can see the continuity of both solutions over the parent grid and over the child grid. So for this test, these are the keys, vortex, and MB2, and GRIF, and active 2 So after this validation of the development, the idea is to build a grid refinement strategy for the Gibraltar region. Here with two grids. To include the intense energy transfer region here at the center of the strait, and to see how this energy is upscaled to the large scale flow, and how it is interacting with the tides or with the scale circulation. So the parent grid is a low resolution grid here in red. This DR4 domain covered a wide area from Portugal to the exclave of Melilla in the Alboran Sea. And we have two child grid, high resolution grid featuring all the strait here with a resolution of 180 meters. And the second child grid with a very high resolution with Shear 4 and is located just over the Cameron Sea. You have the grid evolution there and the number of points and the time step associated to the grids. For the nesting, we use the NestG graphical interface, which is released in the CROCO toolbox. We use the same input fields for the bathymetry, which is the same high resolution product presented before. Slides are interpolated from TPXO multi-resolution atlas. Initial and lateral conditions are interpolated from Copernicus Marine Service forecast or analysis. And bulk and surface fluxes are interpolated from the GFS forecasting system. Finally, land and sea mask is built from the shoreline dataset from NOAA. And we have done some minor modification to the CROCO tools routine to implement this nesting. For instance, for reading just into lateral forcing or tides. And for Lancy mask, we use the Fortran code by Shepard-King and the edit mask interface from the CROCO tools to ensure continuity between all the codes. So from the GPTO project, we show some results here. We have evaluated the impact of the grid nesting of one or two domains in the NBQ approach. So we have performed a sensitivity experiment with no nesting, applying only the NBQ module over the low resolution BR4 domain. This is the full domain covering mainly the Strait plus the Gulf of Cadiz and the Alboran Sea. And we have an experiment with one child grid with a two-way exchange, including updates of NBQ variables. This is a RIA2 experiment. And we have the same experiment with the latest grid, this one, VHR4, over the Camarines seal. And the preliminary investigation we are doing are focusing on the sea level, as tides is the first order large-scale process and also a direct driver for the internal solitary waves. And then we'll have a look on the impact of this upscaling on the surface current divergence, as it is a proxy of surface signature of internal solitary waves from space. So first of all, we present sea level comparison on the 19th of October 2020. This is during our campaign over the Strait of Gibraltar. So we compare sea level computed from BR4 here and the RIA2 models with respect to near real-time observation in green. So model is in blue and the observation is in green in both simulation. And you have Sagres tide gauge station, which is in Portugal. Albufeira is still in Portugal, and then Tarifa in the Strait, provided by the Spanish organization Puerto del Estado. Adding green nesting here, you can see we have a time lag reduction to observation. You can see this one, and then you reduce the time lag between model and observation for these two stations. And you can see that also the tidal amplitude is lessened in this RIA2 simulation. So these two elements combine in a reduction of 10 to 15 centimeters of the Ross mean square error of the sea level, from 45 centimeters to more or less 30 centimeters of these two stations. In Tarifa, inside the strait, there is no loss of variability, and the time lag with respect to observation increases. If we compare now one grid nesting, then a simulation with two grid nesting, you can see the impact of adding the second embedded grid child over the Camarine sea level. In this RIA3 simulation, we have an increased sea level variability from the model, from Sagres and Albufera. And then we have a mean square error reduction of 50% from this one to this one, leading to about 15 centimeter square error. There is no significant change here in Tarifa. So the gain of energy may be the expected sign of a better transfer of energy. Now we have full resolution of the internal modes and the internal instabilities that are occurring over the Camarine sea. So there is no positive change for Tarifa, which is not explained yet. This figure now illustrates the divergence of the surface current in the Strait of Gibraltar, as I said, as a proxy of surface rugosity, which can be retrieved from SAR observation. Still on the 19th of October 2020, during the campaign. And this figure illustrates the divergence of the surface current in the strait at the intermediate high resolution, Shear, which is about 180 meters. So if we compare both the two systems with one child and two child grids, we can see more fine scale over the generation area at Reional, and with more intensity in this model than in this one. You can see as well minor differences between the two models on the pattern of the internal solitary wave at this eastern end of the strait. This is maybe due to an advance in wave propagation in this model. If we present now results at the low resolution between BR4 and the RIA3 model at the resolution of the parent grid, this is, I mean, you have upscaled all the physics and updated the low resolution parent grid model after taking into account all these processes that have been resolved in the child grids. So this is the same resolution, but you can see you have a totally different scheme of propagation of the wave. Of course, here even you are in an NBQ configuration, you don't have the resolution enough to have the wave propagation. Here you have the results and the signature of these waves. So more fine scales, more energetic at the surface, even at a low resolution. And you can observe now that you have a feature that is what is expected as a propagation of the solitant, not here. So in conclusion, the CROCO NBQ non-hydrostatic module is ready for us for realistic runs, analyzing events even in real time. We have used this capability for forecasting during the Gibraltar campaign. It features enhanced physics for LES and DNS problems, and nesting capability for studying scales interactions. Of course, we still need observation to validate all these findings. That is the object of new campaigns coming soon, and we'll continue our investigation over the Strait of Gibraltar. In particular for the large scale upscaling of this small dynamics to study the impact of all these small scale dynamics now for the circulation, for the tides, and even at a climatic time scale. From a development point of view, the future evolution will concern the surface and inner ocean hydrodynamic, non-hydrodynamic coupling. Also the bottom interface condition, as we want to study acoustic gravity waves, as well of some physical and numerical acceleration of the code, in particular using GPU. So that's all for me. Once again, thank you for the invitation and for us to see what we are doing. And if you have any question.
Thank you, Laurent. I will stop the